Hi, I'm Professor Melko, Chemistry PhD, and your university chemistry professor. Today we're going to do some practice problem on ionic bonds, covalent bonds, bond polarity, Lewis dot structures, and molecular shape. Does that make sense?
Yes, that sequence of words I said made perfect sense.
Great, let's jump into it then. So let's start with this practice problem. Ionic bonds. Which of the following statements is true regarding an ionic bond in magnesium oxide, MgO? A, the ionic radius of the oxide ion is greater than its atomic radius. B, magnesium and oxygen bond by sharing electrons. C, magnesium gains electrons, oxygen loses electrons. D, ionic radius of magnesium ion is greater than its atomic radius. So try to answer this yourself, pause the video here and think it out. Otherwise, I'm going to proceed to solve it. So let's take these one at a time. A and D here are about ionic radii. We talked about atomic radii in previous videos. Feel free to go back and watch those. But when it comes to ionic radii, think about adding or removing electrons. Usually these electrons live in shells, right? And the shells get further and further out. So the atom gets larger and larger. If you remove electrons, that atom's going to be smaller because you're removing those shells, okay? So for the oxide ion, you're actually gaining electrons, right? So O wants to be 2 minus. You've added electrons, you've added shells. The radius of oxygen should get larger because you're adding those shells further and further out. You can think of it like extra layers of an onion that you're adding on. The onion gets bigger. Oxide ion is greater than its atomic radius. So A looks correct. Contrast that with D. Radius of magnesium ion is greater than its atomic radius. Okay, magnesium here becomes 2 plus. Okay, 2 plus means you've removed 2 electrons. So you've peeled off some of these outer layers. The onion is getting smaller. Magnesium as an ion is smaller, not greater, than its atom. Okay, so as an ion, it's smaller. D cannot be correct. Letter B, magnesium and oxygen bond by sharing electrons. This would be a covalent bond. That tends to be between things like carbon, sulfur, oxygen, hydrogen. Non-metals only form covalent bonds. Magnesium's a metal, oxygen a non-metal. When these two things get together, non-metals and metals, we form ionic bonds. And that is not sharing, that is a transfer. Okay, so if this said transfer of electrons, that might be okay, but it doesn't, so B cannot be correct. C, magnesium atoms gain electrons. No, this 2 plus means it's lost electrons. So these two are flip-flopped, so C cannot be correct. So the answer must be A. Let's move on. What kind of bond is found in sulfur iodide? Okay, first let's try to contrast covalent and ionic. Pause the video here and see if you can answer that and the rest of this question. Ionic, things from the left with things from the right. Metals with nonmetals. Sulfur and iodine. Here's sulfur, here's iodine. Both are nonmetals, so this is going to be a covalent bond, not ionic. But we can take it one step further. Is it going to be polar covalent or nonpolar covalent? Okay. You can go back and watch my previous video where we talked about covalent, nonpolar, polar covalent, and ionic bonds. But when it comes down to polar versus nonpolar, we consult the electronegativity values. And electronegativity is how badly does an electron, or how badly does an atom hold on to its electrons? How badly does it want electrons? Okay, these halogens really want electrons, and it turns out as I go up and to the right, the electronegativities increase. The atoms want electrons more. So these numbers I've written here are the electronegativity values for these elements. So when deciding if something is polar or nonpolar as a bond, I compare these values, right? If they're different, it's polar because one of the elements wants that electron in the bond more than the other element. And so there will be an unequal sharing of those electrons, which is polar. Here, though, sulfur and iodine both have the same electronegativity value, okay? So at least based on this chart, they equally want the electrons in a bond. So if there's a bond between sulfur and iodine, they want those electrons in this bond equally. So there will be a completely equal sharing of these electrons. Now, that might not be 100% accurate if you can draw exactly where the electrons are, but based on these electronegativity values, that's how we sort of decide these things. Here the numbers are equal, so there's a completely equal sharing and this would be nonpolar covalent. Okay, if sulfur was bound to fluorine, fluorine has a much larger electronegativity value, so it would hog the electrons. That would be a polar bond, and a very polar bond between S and F. But between S and I, sulfur and iodine here, it's going to be nonpolar covalent based on these electronegativity values, which is how I'm teaching it for the current course. What about this one? Use the same strategy and try to answer this. What bond is more polar, PF or PCl? Okay, P's electronegativity value is 2.1. F's electronegativity value is 4.0. Cl's electronegativity value is 3.0. So clearly, PF is a polar bond and PCl are polar bonds because phosphorus is less than each of these numbers. So both fluorine and chlorine are going to hog the electrons in that bond from phosphorus. So both are polar. Which one's more polar? Well, it depends on the difference of these numbers. 4 minus 2.1 is 1.9. That is larger than 3 minus 2.1, which is 0.9 for chlorine and phosphorus versus phosphorus and fluorine. So the larger the difference, the more polar it is. So here the answer is PF. That is a more polar bond than PCl. Now, some of the hardest concepts in this section of material I've taught, go back and watch the previous couple of videos in this lecture series, are Lewis dot structures. We've talked about these in the past, how to draw a Lewis structure for an individual element, but when you form molecules, there's sort of 5 steps that you go through drawing these Lewis dot structures. Again, go back, watch the videos, figure out those 5 steps. Once you've done that, come back, pause the video here, and try to draw this Lewis dot structure yourself. I'm going to solve it in another second here. So, step 1 here is to count the valence electrons. Everything in this column here has 6 valence electrons. Oxygen has 6, sulfur has 6. So the total valence here is 6 for sulfur, plus 6 for each oxygen is 18. So 6 from sulfur, 18 from oxygen, a total of 24 valence electrons. Okay, that's the first step. The second step is to draw the central atom with 8 valence electrons around it. And I know sulfur is the central atom here because it comes first in this formula. Okay, so there's my central atom surrounded by these 8 valence electrons, where each valence electrons is symbolized by this dot, hence Lewis dot. Now the third step, add the other atoms. There's 3 of them, doesn't matter which 3 sides I pick, just don't put them all in the same side. Okay, so here I'm picking east, west, and south to put my 3 oxygen atoms. Okay, and I'll start surrounding these with the additional electrons that I have. So far I've used 8 electrons, these 8 dots, so now I'm down to 16. So let's start filling the octet, and I'll draw this a little bit closer here. Let's start filling the octet of this oxygen. 2, 4, 6. So now I'm down to 10 electrons. Notice I stopped at 6 because I already had these 2 that oxygen has access to. So now both sulfur and this east side oxygen have 8 valence electrons each. Both are happy with their octet. This oxygen on the south side of sulfur here, I'm going to complete its octet. 2, 4, 6. So now I'm down to 4 electrons left, and that oxygen is now happy. I try to complete this last oxygen's octet. 2, 4, but oh no, I've run out of electrons. I have no valence electrons left. I can't draw 2 electrons up here because I don't have them. I've run out of all 24 electrons. Okay, so that's step 3. Step 4 is if you run out of electrons like this, move electrons from the central atom to electrons that are not bound to anything else, right? These are bound to an oxygen. The ones on the bottom are bound to an oxygen. But these ones up top are free. I'm going to move those in between so that this oxygen that is deficient now has access to those electrons. And once I move it there, now this oxygen has access to 1, 2, 3, 4, 5, 6, 7, 8. And likewise, the sulfur still has access to 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is how I satisfy everything's octet here. I move these electrons off the central atom in between the deficient atom and itself. Okay, so now all the dots are accounted for, and now I can replace a pair of dots, these bonding electrons, between two atoms, not lone pairs like this, but the bonding ones I'm going to replace with a solid line to signify a chemical bond. So one for the oxygen to the east, one for the oxygen to the south, and there's 4 electrons, or 2 pairs, so this is a double bond here. Okay, so for the formula SO3, this is the Lewis structure. There's a double bond for 1 oxygen and 2 other oxygen single bonds. Okay, sometimes you'll talk about resonance, which is just the fact that I could have equally drawn the double bond here, right? There's nothing special about the oxygen on the left versus the right. Okay, so sometimes you'll be asked to show all 3 of these possibilities, which is to say there's resonance, there's 3 different sort of resonant forms of this same molecule. Okay, last problem I have here is molecular shape. And these ones are harder still because you have to draw the Lewis dot structure like we've just done, and then assign it to some geometry. So feel free to pause the video here, try to draw the Lewis structure, and then assign it to a molecular shape. Feel free to go back and watch the previous videos I've posted on how to assign molecular shape and how to draw these Lewis dot structures. Pause the video here and give it a shot. So let's draw the Lewis dot structure. Again, step 1, count up the valence. 6 from each oxygen, so there's 24 from that oxygen. There's 6 from each sulfur, so there's 6 from that, for a total of 30. But don't forget about the charge here. That 2 minus means there's 2 extra negative charges, or 2 extra electrons. So it should be 32 valence electrons total. The central atom is sulfur, surrounded by 8 electrons. Now I'm down to 24 valence electrons. And I have 4 oxygens, 1 for each side. Draw these a little closer here. 1 for each side of the sulfur. And I'll start adding electrons in for each oxygen. There's 6, down to 18 electrons left. Here's 6 more to make the octet for the oxygen on the south, dropping me to 12 electrons. Now the oxygen on the west side gets 6 of its own to get to an octet, and I have 6 left, perfect for this last oxygen. So here I ran out of electrons right on time. Everything has an octet. I don't have to move electrons off the central atom. I'll just end by replacing these bonding electrons, those between 2 different atoms, with lines. So here's the Lewis dot structure for SO4. If it has a charge, usually I'll draw it in brackets and put the charge up here, just so people know that this has a 2 negative charge overall. Okay, so that's the Lewis structure for SO4 2-, the sulfate ion. Okay, now you have to worry about how many bonding and non-bonding electrons are on the central atom. Okay, bonding electrons are these between various atoms, or between 2 atoms. Non-bonding would be a pair like this on the top oxygen, okay, where it's not bound to anything else. But we're only considering the central atom here. Sulfur has 1, 2, 3, 4 pairs of bonding, so 4 bonding pairs, and 0 non-bonding pairs. Sometimes you'll be given a table to consult what molecular shape this is, or perhaps you have to memorize it for some classes. For this introduction to chemistry class that I'm currently lecturing on, they sort of get a table. So here, 4 bonding, 0 non-bonding means this is a tetrahedral shape. And that would be the final answer here. So you have to draw the Lewis dot structure, worry about bonding and non-bonding pairs on the central atom, so here's sulfur, and then determine the shape based on those bonding and non-bonding pairs. Okay, so that'll do it for the practice problems here. If you like these, please feel free to like the video and subscribe to my channel on YouTube. And you can look for more lecture videos like this coming in the future. Feel free, as always, to go check me out on Twitch, where I have weekly office hours, usually Tuesdays and Wednesday afternoons. You can come by and ask whatever chemistry questions you might have. That'll do it here. I'll see you next time.